Okay, folks, moving on to our next learning goal, we're going to discuss the colligative properties, which you've done in general chemistry. So I'm only going to touch on a few of these, namely freezing point depression and boiling point elevation. But we should also note that osmotic pressure or osmosis is another really important with respect to the colligative properties. But as I said, I only wanted to draw our attention to freezing point depression and boiling point elevation as it connects to what we've been discussing in phase equilibria. So let's take a look at the chemical potentials. And if you recall last time, we wrote down what the chemical potential is for a solution. And it goes as the following. The chemical potential of the solution will equal the chemical potential of pure material plus RT times natural log of the mole fraction of that material. And of course, this is assuming that it follows ideal solution behavior, right? Which would say P vape of the solution equals the vapor pressure of pure A times the mole fraction of A plus the vapor pressure of pure B times the mole fraction of B. Now, generally, with respect to the colligative properties, colligative refers to the statement depending on the collection, okay? And we also typically think about this with solvents and non-volatile solutes. So I'm going to cross that out and say that goes to 0. PB star equals 0. So that is a non-volatile solute. So something like a salt, for example. Okay. So depending on the collection really means just depending on the amount of solute present. And what I want you to take stock of here is because chi A now will always be less than 1, so chi A will always be less than 1 for a solution. That means this natural log will always be negative, and thus, if you see the figure, the chemical potential of the solution will always be lower than the chemical potential of the pure liquid. So I'm going to highlight those, so the solution in red and pure liquid in blue. So you can see here, right, that the chemical potential is lowered. And so what that means now when we look at the curve crossing here, this is only affecting the liquid, right, through its vapor pressure. So no effects on the solid chemical potential, but now you can see the solid chemical potential is going to cross that line at a lower temperature than normally would, so the freezing point is lowered. And now you can see that the liquid chemical potential, or really I should say the solution chemical potential, crosses the vapor line now at a higher temperature owing to boiling point elevation. Okay. So we can see that that's true with the chemical potentials, but let's flush that out a little bit more in more details. Okay. So we noted chemical potential of the solution will be less than the chemical potential of the pure material. But now what we would also learn if we go through detailed analysis of the phase transitions, the delta H of vaporization of the solution must be larger than the delta H of vaporization of the pure material. And we can see here in this calculations that I've done that is, did I have that labeled? I just realized, I don't know. Haha, I know what I figured out. Okay, let's keep going with this. Haha. So the delta H of vaporization of the solution is greater than the pure delta H of vape of just the pure liquid, right? So what that means is the vapor pressure of the solution for any given temperature has to be less than the vapor pressure of the pure material. And that's why I was confusing myself. So we can see that here on this graph, right? Where this is the Clausius-Clapeyron line, so the phase boundary between the liquid and the vapor. And you can see in blue here universally the vapor pressure of water, of the pure water, is greater than that of the solution, right? And so that's due to this chemical potential interaction that we just discussed. Another thing that we can think of why that must be true is, now when you look at this cartoon that I have, you can see here that these ions are going to interact with, in this case, water, our solvent, in a way that kind of locks those molecules in to the solution, right? So the interactions between this polar H2O molecule and this ion are quite strong. They are stronger than the interactions of just water and water. And we can see the same thing for the anion. So that has the effect of increasing the delta H of vapor of the solution. So we have to put more heat into liberating these molecules. As a result, for a given temperature, the vapor pressure of the solution will be lower. So not as many molecules are able to evaporate. Correspondingly, the boiling temperature of the solution must be greater than the boiling temperature of the pure material, as noted with the chemical potential example. Okay, so similarly now, we could also see, like if we highlighted where atmospheric pressure was, about 760, we note that the liquid boils when its vapor pressure equals atmospheric pressure. So you can see here the pure water crosses that line before this aqueous NaCl solution will, right? I had to extend that line. So we can see once again boiling point elevation. So what about the freezing point depression, right? So we already talked about that. So let's say T freeze of the solution will be less than T freeze of the pure material. And that's because the presence of these ions hinders the solvent's molecules' abilities to find each other and form that crystal structure corresponding to their solid configuration. So the solution is able to persist in the liquid state at lower temperatures because these ions are disrupting their network. All right? So if we think about this quantitatively, there's a couple ways that we can write these equations. So for boiling point elevation, I'm going to write that as delta T boil. And because that's a boiling point elevation, that's T, let's see, so that'll go T solution, I'll just write T solution minus T of the pure material. So that quantity will always be positive. And so empirically, or not empirically rather, but through derivation, this quantity can be written as the following. So the mole fraction of the solute times the quantity RT squared, where that's the boiling point of the pure liquid, divided by the delta H of vaporization of the pure liquid. Okay. So now similarly, freezing point depressions are always negative. So if we say T solution minus T pure liquid, we can then write the following, which is established through derivation. So that goes mole fraction of the solute times RT squared. And now that's the, all right, fusion, so that's the freezing point, right? Divided by delta H, fusion of the pure material. So these are like derived using our ideal situation. And then now you'll notice here that I've got some constants down here. So in practice, these are actually calculated using the following constants. So the molality of the solvent times the boiling point elevation constant of the solvent. I'm just checking my notes to make sure that I've got that written down correctly there. Okay, let's see. Yes, so, oops, that's, apologies. That's why I checked. Molality of the solute. Okay. Molality solute times this boiling point elevation constant, which is empirical. So it's measured, it's determined through measurements, right? And similarly, the freezing point depression constant is often given as m solute times kf, where again, that's another empirically determined value based on the solvent. And so you can see I've listed a few values there. So this is a situation where we rely much more heavily on the empirical value than the idealized value, because as it were, these kinds of solutions that exhibit colligative properties are generally non-ideal solutions. So we like to use these equations that contain the empirical constants more so than those derived quantities. Okay, that's all I'll say about colligative properties. I'll see you in the next video.